Hi, this is Betsy Scott, Manager of the Best Practices Research Alliance. Thanks for your interest in our webinar, 1 year later, results from the Energy Efficiency Lab Home so far. This session is brought to you by the Best Practices Research Alliance. It's our innovation network of builders and manufacturers throughout the country who are interested in improving home quality and performance. The session is made possible in particular due to the support of the Alliance sponsors, who you see the bottom right-hand part of your screen, certainly as well as the U.S. Department of Energy's Building America program, which is the key funding partner for our Energy Efficiency Lab Home. During this, the third segment of the webinar, we will again provide the quick overview on the lab home as a project. Anthony Grzolya will give that information. And then we will be sharing a look ahead at what we'll be doing over the next several months in terms of research in the areas of domestic hot water and the thermal enclosure performance. And that will be led by Nick on the domestic hot water front and Anthony in the thermal enclosure. And then we'll wrap up by sharing some additional resources that you can find related to the project online. So I'm going to turn the mic over, if you will, to Anthony Grzolya.
All right, thanks, Betsy. So we, as Betsy said, we worked with SNA Homes. Probably it was in 2010 when we were building the home. The home is built in just north of Pittsburgh, about 10, 12 miles in Ohio Township, and the community is called Cobblestone. We picked SNA Homes because they were a Building America partner with us, and they knew what some of the strategies we were trying to shoot for on several projects before this, so they had a good handle on some of the aspects that we want to implement in this home. But what we did was we took their typical floor plan that they construct multiple times, and we want to use that plan and convert it to a net zero energy home. So what we did was, in general, the home is basically almost net zero energy, very close to, but the home basically has, on the thermal enclosure side, it has an R10 sub-slab insulation, R20 foundation, R40 walls, and an R60 roof. The home looks like any other home in the subdivision, so nothing drastically different. If we can move on, that's the next slide. Some of the purposes of this home was, again, through the Building America program as part of the research funding that they've provided, but three key factors. One of the purpose is to obviously have a very high-performing home. So looking at the enclosures, the mechanicals, the hot water, and lighting, we want to reduce the amount of energy consumption we can in the house by basically implementing the higher end of these systems. Then the other part is how easy are these systems or components in this home easy to construct. And we went through probably 5 to 6 months of just trial and error and modeling efforts and looking at different systems regarding wall performance, regarding mechanicals, and we selected different systems in regards to performance, constructability, and cost. Obviously, cost is probably the most important piece to this project, so we wanted to make it as affordable as possible. So some of the research that you'll be hearing in the next 25 minutes will sort of address some of those systems.
So go ahead, Nick.
Okay, so how do I get this to you? Okay, so first it's we're doing some. We're looking at a de-superheater and the performance of one in the home. This diagram indicates a typical ground source heat pump, with the exception that we have a de-superheater that's located between the compressor and the condenser portion of the refrigeration loop. And the de-superheater basically takes some of the heat of compression away from going down into the ground, particularly during the summertime, and reclaims that heat in the form of with the use of a heat exchanger, and that heat is we're able to use that heat to generate domestic hot water.
So this is the plumbing side of the de-superheater, and as you can see here, we have a two-tank arrangement where we're going to the first tank, and then it can go, cycle back into the second tank. We have the valving so that we can either have a two-tank arrangement or a single-tank arrangement. You'll note the drain water heat recovery equipment that is it's installed but currently not being utilized in the home. Okay. So here is a photograph of the equipment as it's installed. To the right is the ground source heat pump, and then the two tanks. So we submitted a draft plan for short-term testing to NREL, and where the research questions that we're going to address are, we want to determine if the heat pump de-superheater operates as predicted in the Transys modeling. The second objective is, what is the efficiency of the water heating system for each equipment mode? So whether it's a two-tank versus a one-tank, and which one makes sense to use. And then the third research question is, quantify the impact of de-superheater operation on the measured heating and cooling COPs of the ground source heat pump. How does this affect this efficiency? And as part of doing some of this testing, we had to do some changes to the instrumentation as well as the Transys modeling to make the short-term testing more, have it done easier. So some of the things we're looking in short-term testing are the ground loop inlet and outlet temperatures, the domestic hot water supply and return temperatures, the de-superheater supply temperature, the de-superheater supply temperature in the heating mode and the cooling mode, and the flow rates, as well as the return air temperature of the unit, and the what staging are we at as far as the compressor and the blower. So we want to know what the unit's doing with all these other parameters. So that's what we're going to be doing for domestic hot water.
So Anthony, what are we looking at for thermal enclosure performance?
All right. Well, moving on from the mechanicals, we're going to talk a little bit about thermal enclosure. Obviously this house is very airtight, and like I said before, the walls are R40 walls, basically from outside to inside. We have vinyl siding, house wrap with all water managed details, flashing and so forth. Then we have 2 inches of XPS foam on the wall, and then we have basically a 2x8 wall with staggered 2x4 studs, and that is insulated with JM Spider insulation. So very thick wall. And what we want to learn is, how do these walls manage moisture from within the home, and are we going to see any condensation potential in these wall cavities? So basically, over the last 18 months, we installed occupants. Well, they're really not occupants; they're devices. And as you can see in these pictures, we installed humidifiers, we installed radiant heaters in many of the rooms and bathrooms to simulate occupants. Basically, their breathing and their heat that they give off, and we're simulating cooking events and shower events. So over the last 18 months, just from general looking at the data on relative humidity, in winter, our ranges are between 27 and 49% RH, and in the summer, they range between 38 and 55. So, they're probably slightly higher than a traditional leaky home, but obviously this home is really airtight, so a lot of that moisture is being retained in the home, and so that's something, with high-performance homes, that's one of the research ideas that we have is, how well can these homes manage moisture, and what types of strategies are needed to control these environments. So Basically, this is the floor plan of the home. We have every wall is monitored. There's an array, so every orientation of the home has an array. Basically, there's 4 different locations. 2 of them are just in a field of a wall, so in a cavity, and the other 2 we're actually looking at. The home was framed, was panelized, so we're looking at panelized connections in those cavities. When you have thermal bridging of the 2 panels coming together, what does that do to the condensation potential? And also, we're looking at between 2 windows where you have a little bit more framing. What does that do in those cavities in regards to condensation potential? Move on. So what we did over the last several months was we looked at, over the last 18 months, sorry, we looked at just general observations when we go into the home, when we look at the monitoring data and so forth. But what we observed over the last 18 months was we haven't seen any signs of condensation on any interior surface, whether it be on the foundation, the slab, windows, drywall, baseboards. No evidence of condensation, so that's a very good thing. But what we really want to know is what's happening within the walls. What we did here was we developed a tool, condensation analysis tool. It's basically a dew point analysis tool that we developed, and we wanted to run just a simple model. And as you can see here, where my arrows are pointing, this wall system that we installed is on the borderline of being an acceptable solution, and that's basically what we're saying is because of the amount of cavity we have, the thickness of the 7.5 inches of fiberglass, obviously that insulation is keeping that first condensing plane a lot colder. So that's where we want to find out, are we actually seeing any condensation or are we not? So looking at the data will help us better understand some dew point analysis tools and also some WUFI analysis tools, which we've modeled also, that gives us some indication of some slight risk. But then we also want to understand is if there is some instances of condensation in these wall cavities, how quickly does it dry out over time? So that's one thing that we want to try to learn. So within these walls, these are the types of arrays that we have. So each array or each orientation of the wall has an array within the cavity and an array on the stud itself. So basically we're measuring humidity, moisture content, and temperature in all these areas, all the areas of the OSB and of the stud surface. So we really, the next 6 months, we're going to try to look at this data. Currently, we're not funded to do this research, but we do want to continue looking at the enclosure and try to give us some more insight on the home in general. Some of the other areas we're looking at is windows and door surface temperatures to understand, is there any condensation potential? Like I said, we did not observe any condensation, but how close are we to the interior dew point? Are we 2 degrees off from condensing, or are we 10 degrees off? So these are the things we're trying to understand right now. And then lastly, where all this data is being fed through all these wires in this home, and now we have to basically go through all these lines of data and graph them and start reviewing them. So basically within 6 months' time, hopefully we can have another webinar and present you some findings on the thermal enclosure.
If you're looking for additional information on the Energy Efficiency Lab Home, there are several presentations available on the IBACOS.com website via the link Our Work/presentation. We'll also, in the next couple of weeks, be posting some detailed research reports that we've delivered to the Department of Energy's Building America program on the project. You can also visit the Research Alliance website. There's a special section on the lab home, including some high-level overviews of each of the technical systems in the house, in general what we were trying to accomplish with the project, as well as an in-depth in the news section that features a lot of articles that we've posted recently through EcoHome, Professional Builder, Energy Design Update, and other publications. Thank you again for your interest in the Lab Home webinar. If you aren't yet a member of the Alliance and you're interested in innovation as a home builder or manufacturer, be sure to visit our website, and for more information just click on the Contact Us tab and we will get back to you.
Lab.